ocean and climate change. This is the team of people I worked with. Rick Smith, me, Peter Gent, Jim McWilliams, John Dugwitz, and Bob Malone. Other scientists I worked with are Frank Bryan, Matthew Hecht, Steve Griffiths, Anne-Marie Tregier, Richard Greatbatch, Daryl Home, and Li Liang Fu. The ocean seems remote, unchanging. The truth is it's constantly changing, and those changes affect us every day. Huge currents crisscross the world. They carry heat across the planet, controlling temperatures and weather patterns. There are over 100 major currents and thousands of minor currents. My job was to simulate the world ocean. Ocean currents affect our lives every day. For example, the Gulf Stream carries warm water from the equator to the poles. It swings by South Carolina on the way, and that's why it's so warm in Greenville. London is at the same latitude as Calgary, Canada, but it's much warmer because of the Gulf Stream. Currents spawn eddies, whirlpools of water that contain most of the energy in the ocean. Eddies are the weather of the ocean, like high and low pressure systems in the atmosphere, only smaller. Stable currents contain hundreds of small eddies that come and go. To model the ocean and predict its behavior, we have to model those eddies where most of the energy lies. Ocean modeling is a grand challenge problem, like mapping the genome or curing cancer. It's so difficult because the ocean's spatial scales are small, but its time scales are long. Each eddy is only 10 to 100 miles across, but the ocean's changes happen over long periods, centuries, or even millennia. The atmosphere is easier to model because its eddies, the high and low pressure systems you see on TV weather maps, are large, 100 to 1,000 miles across. But its changes happen over just days or weeks. How do you simulate a system so big when its component parts are so small and its timescales are so long? The model must deal with many, many small components, but over a long time. This means the amount of computing is very large. Before supercomputers, it simply wasn't possible. We divide the ocean into small cubes called the grid or mesh. Then we select a time interval. The computer program moves through time, calculating the change in every cube from one time step to the next. The smaller the mesh size, the more accurate the model's predictions, but the greater the computing requirement. Cutting the resolution in half multiplies the computing time by more than 8. We need to simulate every eddy if the model is to represent reality. Many earlier attempts failed because their mesh size was too large. That is, their resolution was too low, like a fuzzy TV screen. So if we make the mesh size too fine, the computing time will be too great. To be useful, the model must compute much faster than real time on today's computers. So the important question is, how small does the mesh size need to be to simulate every eddy? This chart shows the mesh size versus the scale of the eddies. The upper lines show the average eddy size at the various latitudes. Notice they're larger near the equator and get smaller going north or south. Those are harder to simulate. As we make the mesh size smaller, we move down the graph and our ability to simulate the eddies improves. At 1/10 of a degree, we can simulate the eddy field at all latitudes. Another test is the calculated mean kinetic energy versus eddy kinetic energy. Kinetic energy is the energy in something moving. For example, a moving car has kinetic energy, a stopped car doesn't. The ocean's water is moving, and the kinetic energy in the eddies is about 70% of the total kinetic energy. The bars on the right show that. It's how the ocean actually is. But at the mesh size 4/10 of a degree and 2/10 of a degree, models weren't showing that. We were able to cross a threshold at 1/10 of a degree. Beyond that, the results aren't much better. So we're able to map currents fully and accurately for the first time and without extending the computing time unnecessarily. For example, no one had been able to model the Azores current, which flows from North America to Gibraltar. Now the model matches reality in both strength and position. The top image shows the turbulence of the Azores current at one moment in time. It's wild and chaotic. The bottom shows the average turbulence over 3 years. It's smooth and matches the observation. We were able to cross a threshold to resolve the eddy field by using incredibly powerful computers. The thinking machine's CM5 was capable of 131 gigaflops. That's 131 billion calculations per second. This is the Gent-McWilliams parameterization, the most important breakthrough in modern numerical physical oceanography. John Dukowitz and I were able to add this parameterization to our model, making further improvements. The highlight of my career was this paper called the Anisotropic Gent-McWilliams Parameterization for Ocean Models. The technique it described allowed the Gent-McWilliams parameterization to be used in eddy resolving 1/10 of a degree simulations. This had been tried before, but the simulations were not stable and the eddy fields were strongly damped. This paper allowed eddy resolving simulations to run stably. One of its successes was that it cleared out the extra noise in the model of the Kuroshio current and let us map it clearly for the first time. With earlier grids at lower resolution, models showed an eddy off Japan that doesn't exist. There's the eddy that doesn't exist. The next refinement made it smaller, but it didn't eliminate it. Finally, with the Gent-McWilliams parameterization, the Kuroshio current matches reality. The Japanese were delighted with that. This is how the Kuroshio current actually looks. Then we're able to model the entire ocean much more accurately. This is an important step toward the ultimate goal of long-range climate forecasting. This video shows the model's output. Red is the warmest water, blue the coldest. Notice the tropical instability waves moving across the middle from South America to New Guinea. Also notice the Gulf Stream off North America, the east coast of North America, the Kuroshio current off Japan. These are western boundary currents. The Gulf Stream is in the Atlantic Ocean and the Kuroshio current is in the Pacific Ocean. You might also notice the Agulhas retroflexion here, where currents coming off of Madagascar and there's strong recirculation right here, which flows into the Antarctic circumpolar current. The Antarctic circumpolar current is shown in light blue near the bottom. It is the only current that flows all the way around the planet unimpeded by land. It is also the world's largest current in terms of total volume transport, 100 spheredrips, where one spheredrip is 10 to the 6 cubic meters per second. So why does any of this matter? The climate is changing. We can argue about why it's changing or how fast, but some facts are clear. Usually the ocean changes currents and temperatures on a time scale of centuries, but now it's changing faster than we've seen before. There will be consequences. The latest measurements are in. Here's the Greenville News in January 2015. 2014 was the Earth's warmest year since temperature records have been taken. They come from two independent sources, NASA and NOAA and the Japanese Meteorological Agency. And we have known El Nino, which has a temporary warming effect. This is the most important thing I want to say in this talk. It is crucial to find another form of energy than the burning of fossil fuels, which dump carbon dioxide into the atmosphere. CO2 acts like a blanket over the Earth that prevents sunlight from being reflected back into space. This warms the planet. If we do not find another source of energy, we cannot guarantee the survival of our species to our children and grandchildren. This is the famous hockey stick graph from 1999. The blue curve shows the temperature of the Earth over the last 1,000 years, and the red curve shows the carbon dioxide in parts per million in the atmosphere over the last 1,000 years. Notice that both curves increased dramatically in the last 200 years due to the Industrial Revolution, where mankind started dumping lots of carbon dioxide into the atmosphere. This may overstate future warming, but we know warming is happening, and we need to understand it. That means we need to understand the ocean. That means we need to understand what's coming. To do that, we need a model of the climate that can compute every element of our changing planet. My ocean model is a key part of that larger model, the Community Climate System model, now being used by many governments, international businesses, and climate groups around the world. As the combined model gets better, we'll be able to do useful predictions, for example, of El Nino. Why does that matter? El Ninos cause great damage to populations and agriculture around the Pacific and affect the weather in America. Predicting them would allow people to prepare and greatly reduce that damage. It could even save lives. My colleagues at Los Alamos and NCAR in Boulder have continued the ocean model's development. The ocean holds the answers to so many mysteries about our world and its future. Finding those answers has been my life work. Thank you very much. And one final thing I want to say is I appreciate the time that both my son and my father spent to making this presentation what it is. Thank you. For any comments or questions, please email me at rdsmith864@gmail.com. Thank you.